right, lesson 6.2. We just got done doing the Goff problem as our warm-up, so let's see who got this right.
You got golf.
Thank you. I just thought of that. Okay, so my hint was that you could rewrite this. Goff is the same thing as g of f of x. So, and then I told you yesterday, if it helps you to like fill in what f of x is, you can do that. F of x is 3x plus 2 in this case. I'm getting that from here. All right, so we're going to plug 3x plus 2 into g. So g is 2x squared minus 1, and I'm plugging in 3x plus 2. Okay, if you got that far, that's great. That's Goff. Now we just got to simplify this and write in standard form. Okay, if it helps you to write this out, please do. Don't distribute the exponent. All right, so this would end up being 9x squared. Plus 6 is plus 12x. Good. Plus 4.
Yeah, I haven't gotten that out yet.
Yes.
Then you distribute the 2. So your final Goff answer should be 18x squared plus 24x plus 7.
Yep, I got it right.
Nice.
I got it right my second try.
Okay, we do a little bit more Goff and Fog in this lesson, so it's important we know how to do that because we use this concept in this next topic. We're talking about something called inverse functions. All right, so I have a little like activity, if you will. And you're just going to think about this in your head for a second. So I'll read this out loud to you. I have 4 pairs of something we call inverse functions. Okay, you don't know what that is yet, but I'm telling you this is what they look like on a graph. And I want you to look at their equations. Okay, so I have an f and a g, f and a g. Now you don't know which graph is which. Some of them you could figure out. And it's nice on mine because they're color coordinated. But look at their graphs and look at their equations and just see what you notice. Don't say it out loud. I'm just going to give you like 20 seconds to maybe jot some things down or come up with some ideas of things you notice in your head. Okay, who wants to share? Justin.
They're opposite or something.
Okay, what do you mean by that?
So like one equation, like the first one is 4x plus 3, and then for the g, it's the opposite.
Okay, I'm just gonna correct your like terminology here. Your thinking is beautiful. They're like inverse operations of each other, is what we call that. Not opposite or super close. But I know what you're saying. So instead of times by 4, we're dividing by 4.
Yep.
Instead of adding 3, we're subtracting 3. Does that kind of work for all of these?
Yeah.
Yeah, this one is kind of confusing to look at it that way. But here, instead of square rooting, we're squaring. Instead of minus 3, we're adding 3. Those are all like inverse operations
What's going on number 2?
of each other. So instead of cubing, we're cube rooting. Yeah. Instead of adding 1, we're subtracting 1. Okay, great. Good. That's one thing with the equations. What about the graphs?
They're like wonky. They look silly.
They're inverse of each other.
Yep, that's what this says.
They're like opposite.
Okay, can you elaborate? Can you put that into math?
It's like there's a mirror. They're being reflected.
Hey, they're being reflected. It's like they're a mirror. Nice, right? Okay, this one's probably, number 3 is probably easiest to picture. It looks like if I were to kind of like, did you guys ever do those projects like in kindergarten where you put paint on one side and then you folded it and then you opened it up and it was like symmetrical?
I mean, maybe. I don't remember my kindergarten.
I remember making snowflakes.
So do you guys agree that if I were to hold...
color these birds. Sorry.
From your desk to the front. There we go. If I were to hold the graph like this, and if I were to fold it, do you guys agree that that blue piece could lie like right on top of my red piece?
You fold it in the middle.
Yep, if I fold it in the middle. Same thing here, right? If I were to fold it in the middle, actually exactly along this line right here, this line is called y equals x. It goes through the origin, has a slope of 1. If I were to fold it right on that line, for all of these, we agree it could just be like reflected over that line.
Sure.
That's another property of inverse function. Some of them are harder to picture than others. Good. Okay, that's what I wanted you to notice. So, in math, we're going to first just talk about inverse relations, and then we'll kind of tie it into functions. But because it comes from this idea that they're reflected over this line y equals x, what happens with functions and their inverses is their coordinates just flip-flop. All right, so think about this. If this point 0, 1 is on my original graph, if I flip-flop that ordered pair to 1, 0, aka all of my x coordinates become all my y coordinates because it's reflected over x equals y or y equals x. So this point 0, 1 is on my graph of the original.
You can use like golf to find those, right? No,
I know what you're thinking. Actually, kind of.
because we did something with like points.
Yeah, like flipping it. Yes.
Yeah.
Okay. So the point 0, 1, if I flip-flop the x and the y coordinates, that becomes 1, 0. That point will be on my graph of the inverse. Okay, and the reason why is because it's just reflected over this line. So all your x coordinates become all your y coordinates. All your y coordinates become all your x coordinates. Okay, that's what an inverse is. Got it? So that's basically what this is saying right here. I screenshotted this from your book. If you have an ordered pair AB in your original function or relation, in this case, like A, and set A here, I have point AB, then its inverse is going to contain BA. All right, so look at these two sets here. A and B are inverse relations. The point 1, 5 becomes a point 5, 1. The point 2, 6, 6, 2. 3, 7, 7, 3. Everybody see that? Okay, you work with inverse functions a lot. Actually, we just, in my AP Calc class, we did something with inverse functions yesterday. So this is important. Another way to think of it is basically all of your domain and range like flip-flop as well. Because my domain just, domain. It's funny, you combine the two words. Domain is my set of all my x values. And my range is my set of all my y values and the set of all my outputs. So those are like literally just going to flip-flop. Okay? All right, let's try one example problem here. So maybe write that right here. Domain and range. Interchange. That's another characteristics with inverse is. Okay. So here's a relation. It's not an equation. They're just giving me a set of ordered pairs that are a part of this relation. It's like a mapping here. They want us to find the inverse of the relation. So the inverse would simply be, we just flip-flop all these points. So negative 3, 4 is going to become what? 4, negative 3. Yep. 4, negative 3. That would be its inverse. X and Y flip-flop. Negative 1, 5 becomes 5, negative 1. 2, 3 becomes 3, 2. What about 1, 1? 1, 1. Negative 2, 1. 1, negative 2. Okay. If I say, like, write this in set notation, I mean with those fancy brackets. So this right here would be the inverse. Now, let's see if that kind of, like, works for these graphs. So in this first one, I have this point right here. This point is negative 1, negative 1. Let's say the red's my original. So its inverse is going to have what point? See how that's also on the graph of the inverse?
Wow.
Okay, all of these coordinates are just flip-flop. Look at this one here. I know we just did one like this. This is 0, 2. 0, 2 becomes 2, 0 on the inverse. That's their relationship. Their x and y just flip-flop. Okay.
Got it.
Got it?
Kind of.
All right, here's some notation with inverse functions. If you see f to the negative first power, have you seen that before? I don't think you have. That is notating, or it's like denoting f's inverse. All right, so if I have a function right here, x minus 4, Its inverse, which Justin noticed this, how it's kind of just like opposite operations, and that's another like characteristic or pattern with them, if you will. Its inverse, I would notate as f to the negative first power of x. What that tells me is that these two, or I guess this x plus 4 is the inverse of this function. Okay? So going back to that little like exploration I had you do, another way I could write g of x is I could say, oh, that's f's inverse. You might see that. Okay?
Got it.
Sometimes they just like call them two different functions. They say, hey, f and g are inverses of each other. But if you see that f to the negative first, that means this is the inverse function. Okay? So here's the characteristics. We already talked about this. Look here, they're just kind of showing you if you plug in 6, you get out 2. So that's like the 0.62. So on the inverse, when I plug in 2, I should get out 6. And I do when they're showing you that. So here's my inverse. When I plug in 2, I get out 6. And I kind of call them like sister points. All right? If the 0.62 is on the original, its sister point or partner point, whatever you want to call it, should be 2, 6. All right. Here's how you're algebraically going to find an inverse, because you're going to have to do this. I'll give you an equation. I'll like give you, hey, y equals x minus 4, and you have to find the inverse, and there's a really easy step-by-step way to do it algebraically. The first thing you're going to do, without graphing, is you're going to reflect it over the line y equals x, meaning you're just going to switch the x and y coordinates. Okay, that's the first thing you do. Switch x and y. What you just did there is you really technically reflected it. All of the x coordinates became the y coordinates and vice versa. And then you're algebraically going to solve for y, for the new y. And the reason why is because that's how we write functions, is we write them as y equals or f of x equals. Solve for the new y. And then lastly, and I'm really picky about this notation, you're going to replace that new y with the correct notation for inverses, that f to the negative first of x. Okay, that's how you're going to algebraically find the inverse. And of course, we'll do it in a couple examples. What you need to know about inverse functions. The x and the y coordinates are flip-flopped. The domain and ranges are interchanged. And there's one more thing, and I can't think of it. Oh, maybe horizontal line test? That's what we're going to talk about next. Okay, before we try an example, there's one other kind of characteristics with inverses. All right, I screenshotted this from your textbook. So if I were to give you a graph and say, is this a function, we would do the vertical line test, right? And if it only hits the vertical line once, at every single possible vertical line, then it is a function and it passes the vertical line test. Now, if I ask you, I don't want to know if this graph is a function. I want to know if its inverse is going to be a function. And think about if you take a vertical line and you reflect it over the line y equals x, it's going to become a horizontal line. So we do something called the horizontal line test. All right. So may I introduce to you horizontal line test, which I often abbreviate it as HLT. And this is to determine if the graph given to you, if its inverse is going to be a function. Not if this graph is a function. If I straight up want to know if this graph is a function, I do vertical line test. If it asks me, hey, is this graph's inverse a function? We would do horizontal line test. And as long as it ever only hits it once, it passes, meaning its inverse is a function. Okay, see the difference? So you got to be really careful with the wording. Look at this example. This blue graph in itself is a function. If I were to do the vertical line test, it's a function. Is its inverse a function? No. Horizontal line, it hits it 1, 2, 3, 4 spots. Okay, so I know its inverse is not going to be a function. See, I'm down to 3 markers.
Oh, where'd the other one go?
That's my bad. It's broken. And we got to order more. All right, let's try a couple examples.
Thanks, red and white.
So I want to know is the inverse of these graphs. So notice how these all say f of x. Well, so this one says y, whatever. Is the inverse of function. So I'm not going to use the vertical line test. I'm going to use the horizontal line test. All right, this one. No. Now, not to confuse you, but let me ask you this question. Is this original graph a function?
Yes.
Yeah.
It would pass the vertical line test. Yep, it would pass the vertical line test. Okay. Is the inverse of this one a function?
Yes.
Yep. What about the circle?
No.
Is the circle a function itself?
No.
No. Ooh, almost put yes. No. Good. The circle's not a function, and neither is its inverse. Okay. Got it? So we're gonna do 2 examples where we're gonna algebraically find the inverse, following these steps, and then we're gonna graph both the original and its inverse on the same graph and see if we can kind of notice this reflection piece to it. So on your homework, I do want you to use 2 different colors when you're graphing these. So if you have 2 different colors in your notes, like a red pen and maybe a pencil, or a red and a blue pen, that's gonna be helpful here. Okay. So let's start with an easy linear equation. Okay, I'm actually going to start by just graphing this line. It does tell me to find the inverse, but we will do that. I'm going to use original graph. I'm going to use blue.
I got my red pen.
All right, my friends, do you remember how to graph lines?
Yeah.
Y-intercept of what?
One. Then go
Slope?
down 1 over 2.
Down 1 over 2. Good.
Yeah, I'm so smart.
Okay, you don't need a bunch of points. Maybe just 4.
That's a lot of points.
Enough to make a straight line.
Also, make my straightest 2.
Okay. I feel like I could do better. It's fine. It's fine.
It's fine.
Okay, it's fine.
I feel that way a lot.
All right, so pick one color to graph the original.
Graph the original.
Graph the original.
No.
Now let me ask you this question. Before we even find the inverse, is the inverse going to be a function?
Yeah.
Yes, pass the horizontal line test. Good. Okay. Now we're going to actually algebraically find the inverse. First step, switch the x and y. Remember, this is just a fancy y. So I'm going to switch the x and y. The y is going to become x. The x can become y. What you really just did, folks, there is you did a reflection. You reflected everything over the line y equals x. There's your first step. Switch the x and y. Second step, solve for the new y. This is my new y, so I'm -1.
Oh, I know.
Now, instead of dividing by -1/2, I times both sides by -2. Okay, so I'm going to go ahead and distribute that. I get -2x plus 2, and I'm going to move it to the other side because that's how I'm used to seeing that. Now, instead of writing y, my third step, I'm going to replace it with that inverse notation. This is the inverse of this f of x. Now, it should look like kind of opposite operations. This one's a little bit harder to see. You can kind of see it like in this step. Instead of dividing by -2, we ended up timesing by -2. Instead of adding 1, we subtracted 1. So you should kind of see those properties that Justin pointed out with the graphs, with the equations of the inverses. Okay, so there's the inverse, and now we're going to graph that as well. So this one has a y-intercept of 2, slope of -2. And you guys were right. The red graph passes the vertical line test. The inverse is a function based on your hypothesis with the horizontal line test. Okay, that's it. Not too bad, right?
Not gonna be that easy.
Okay, we're going to do a little bit harder one. All right. What type of polynomial function is number 2? quadratic. So what shape is it going to make on a graph? Which we call a
Parabola.
parabola. Good. All right. Ooh, Mary Kate did this too. It's going to be a sad face parabola, right? Look at my leading coefficient. So if you're not sure how to graph this, I would just make a table. So I'm going to come over here. This is for my original function. I'm going to call it f. Let's make a table. Now I just chose like nice numbers to plug in, such as like -3, because when I square that I get 9, and then a third of 9, I get some nice numbers. So I plugged in -3, I plugged in 0, and I plugged in 3. Okay, you don't have to do that, but this is just going to be kind of how I graph it. If you really wanted to, you could like complete the square and put this in vertex form. I wouldn't recommend that. I would just make like a quick table. All right, so when I plug in -3, I get 9 times -1/3 is -3 plus 2 is -1. What do I get out when I plug in 0? 2. 0 plus 2 is 2. When I plug in +3, I'm going to also get out -1. And this makes sense because it looks like my vertex is at 0, 2. So let's go ahead and plot this. 0, 2, -3, -1, 3, -1. Does it look like it could form a sad face parabola?
Yeah.
Yeah. I'm going to be pretty lenient. I mean, graphing is important, but like this is enough to draw your parabola. We've already studied graphing parabola, so I'm A-okay with you kind of just getting like 1 point on each side of your vertex. All right, so there's my original function f, or this one is just y instead of f. Doesn't matter. There's my original function. Before I even graph its inverse, is the inverse going to be a function? No. If I were to do the horizontal line test, I see it's failed. Okay, so let's go ahead and find the inverse. So switch the x and y's. Switch the x and y, solve for the new y. So to minus over this 2. Times both sides by -3. So I'm going to distribute that over here. I get -3x plus 6. Ooh, almost done. What would I need to do to solve for y? Square root both sides. Don't forget plus or minus. Okay, so the inverse here, which again I'm going to write with this correct notation. The inverse is plus or minus the square root of -3x plus 6. All right. Now, I think you graph square root curves in Algebra 1. I think. I don't know for sure, to be honest. But you don't have to write this down. They look something like this. You tell me if this looks familiar.
No.
You graph stuff like that?
No.
No. Probably maybe when you guys shut down. Okay. Now, instead of thinking in my head like, how the heck am I going to graph that? What do we know about all of their ordered pairs? Well, careful, not like,
Or like x equals y and y equals x.
yeah, they're like flip-flopped.
Yeah.
Yep.
So negative in the
So this -3, -1
Is -1.
is going to become -1, -3 on my inverse. This 0.02 is going to become
2, 0.
2, 0. This 0.3, -1 is going to become -1, 3. All right, so let's go ahead and plot those. -1, -3, 2, 0, -1, +3.
Oh, this is weird.
I know. So what this actually looks like, here's your square root. Here's your square root curve. It looks like that. But because we have plus or minus, maybe I'll pull up decimals and just kind of show you guys this. Because I have plus or minus, I also have this piece down here. And it is a reflection, so it should be the same shape, right? It should be the same shape. And you guys are correct. If I were to do the vertical line test with my red graph, it's not a function.
Yeah.
The original was a function. Failed the horizontal line test, so we knew the inverse was not going to be a function, and now that we have it graphed, we can see that. that make sense?
We did graph these and ALG 2. I don't remember how to do them, but I know we did them. ALG 1.
Yeah.
Okay.
I guess
That's
my
good.
suggestion would be
Sydney.
just
Yes,
graph the
we did.
parabola like you know how to do, and then just flip flop the ordered pairs.
Okay.
That'd be the easiest way to do it.
Yeah,
Okay.
I have no memory of what.
Let me just quick show you Desmos.
I don't know how.
Yeah.
I remember writing this before.
Well, I remember I just
10
figured out
minutes.
that even if you got like an A for this pass fail, it doesn't even matter. It wasn't waiting to do GPA. So I'm mad that I tried.
No, it's
I maintained all A's, so I'm like I have to do good. I'm like, oh wait, I could have got like a C and stuff.
All right, so here's a
Yeah,
parabola,
I
right?
see.
There's our parent function for parabola. Here's its inverse. Here's the square root of x. Now, see how I'm missing half of my parabola?
Yeah.
That's because I only have the positive version. If I want plus and minus, I need both pieces there,
Oh. Woo.
plus or minus. And there's the true inverse. Because if we do this algebraically, we'd have to do plus or minus of both sides.
Okay.
So that's why it would give us that curve.
Okay.
Now, sometimes there might be like a restricted, like domain. Like it might say only graph like the positive x values, and then you just have to kind of like the piecewise a little bit. You're only gonna graph like the piece it wants you to. I don't know. We'll have to look at some on the homework. All right, so that's basically it for algebraically finding inverses. Switch the x and y. Solve for the new y. We did a nice easy linear one. We did a square and a square root. I don't think they get much harder than the square and the square root ones for now.
Oh my god.
Okay, the next thing, here's where fog and goff come into play.
Oh, there's a next thing.
The next thing says if you're given two different functions, like f and g for example, they are inverses of each other if and only if fog and goff both simplify to be just x. So this plays off of kind of what Justin was talking about. Basically, if all of their operations like undo each other and we're just left with x, in both cases, then they're inverses. All right, so let's try this one. This one says verify that the functions are inverses. So they're telling us that they're inverses, so let's do fog and goff. I'm going to start with fog. Wesley, pay attention to me.
I am. Stop lying with this.
All right, so fog is f of g of x.
Oh my gosh, I remember.
That's fog. So we're going to take g, which is negative 3x plus 3, and we're going to plug it into f. All right, so f is negative 1/3 x plus 1. And we're plugging in negative 3x plus 3. All right, now you have to show me step by step like the algebra here. So what I want to see is, all right, what's negative 1/3 times negative 3, folks?
1.
1x. What's negative 1/3 times 3?
1.
Negative 1.
Negative 1. So what's x minus 1 plus 1? X. Okay, that's good. That's what we need.
Good.
That's basically showing that like all the layers are inverse operations of each other. They
So,
all
like,
undo each other, and we simplified it
Want
just
to get
x.
x every time?
yes. Now we're not done because we also have to do goff.
I was gonna say.
It says both. You have to do fog and goff. All right, so let's do goff over here.
They actually could G-O-O-L.
G of f of x.
Please pay attention.
Okay, so this time we have to plug f into g.
Oh.
All right, g is negative 3x plus 3. So I'm going to plug in
Equals x.
Okay, now, if you're working ahead of me, it does equal x. Here's what I don't want. This is what my kids in Ogongo used to do. They'd be like, oh yeah, that's x. And they don't show me anything. I'm like, you gotta show me. This is x. This is negative 3 plus 3. Ah, that's how I get x.
Got it.
All right. That's a quick and easy way to verify is by using fog and goth. What I don't want you to do, and maybe I even shouldn't put this idea in your head.
Don't.
Okay.
No.
Fog and goth.
Oh.
All right. So let's try a couple more.
Oh.
This one says determine if these are inverses of each other. You can just write yes or no. So we're gonna do fog and goth and see if indeed these are inverses. Okay, but you can't.
Adding and dividing and cube rooting.
I know. I like it. I like that you're looking for that stuff, but you can't. You have to use fog and goth. That's what this theorem says. Okay. Let's start with fog. So this is f of g of x.
So you plug G. No.
Did we start this recording before the fire alarm?
I think so.
Yeah.
Yeah. And they got the fire alarm.
Whoops. I think
He's gotta practice now.
He's got to practice. Runs up at his house.
I can cut that part out of the
No, please leave that in.
I want to come to school tomorrow and say, why is there a fire alarm?
All right, you guys ready for this? This is kind of intense.
Oh god.
It is a
We
little
gotta plug that into f.
3.
All right, so
Yeah,
again,
alright.
take out the x and replace it with parentheses, and then plug in g, which is the cube root x plus 1 over 3. All right, so what simplifies first here, you guys, is I'm cubing a cube root.
Yeah.
So these kind of undo each other, and I'd be left with 3 over x plus 1 over 3. That cube root undoes that cubing, just like squaring and square roots.
And then cancel out the 3 in the denominator.
Yup. 3 and divide by 3. Good. So we get here, which is x. All right, so fog is good, but we have to check goth. If both work, then yes, it's a function. If one of them works and the other does not, it's a no. They both have to work. All right, so now we gotta do
Like-
goth.
If F doesn't work, then you don't have to find off.
Yes, exactly. If fog doesn't work, then you don't even have to check goth. All right, so this is g of f of x.
Could we start with either fog or goth?
Yeah, it doesn't matter. Good question.
What's up, Mary? G.
All right, so here's g, and I'm taking out the x.
So would you cancel?
Bring the bucket.
Yep, hold on.
Hold on, Brandon.
All right, so here's g, and I'm plugging in x.
That's gonna be
3x
That's what I was on.
plus 1.
What kind of cancels out first here?
That's
3.
the one.
The ones technically do.
Oh.
The ones, you have plus 1, minus 1.
Yup.
Okay. So, and again, you have to show me step by step. I know some of these you're like,
And the cube.
Every
the cube
single
over
I understand it.
is 3 over
And the
3.
3.
Then the 3's.
What's fun?
3 over 3 is the same as 1.
Oh! So then it's just X.
And then what's the cube root of x cubed?
X.
Those undo each other.
Oh my gosh.
It worked.
So is, or are, I should say, are f and g inverse functions?
Yes.
Yeah.
Yes.
Indeed.
They are inverses of each other.
Yes.
Yes. Y. E.
Yes.
Yes.
Oh my gosh.
All right, we're gonna keep going because we
No.
might be able to finish this, and then you guys have a whole work day tomorrow. So this is supposed to be a 2-day lesson.
Oh, a whole work day?
So I can just sit around one?
All right, here's another one.
Please
stop. Shut up.
Now, already, based on like what Justin noticed and what Willis was saying on the last one, he was like, these don't look like they're inverses, right? I see this one's
Yeah.
like minusing 9 and this is
Doesn't
squaring.
work. Doesn't
You
work.
can't just say that. We gotta try fog.
Oh, come on.
Watch what happens with fog.
Oh.
So
Oh my
fog is f of g of x.
F of G of X. Okay.
G of x is x plus 3. So we're going to plug that into f, which is x squared minus 9.
So then,
Do not tell me
Was.
x plus 3 squared is x squared plus 9.
Willis,
Willis.
Calvin.
Calvin.
X plus 3 squared is x squared
Plus 6x.
plus 6x plus 9,
Nine.
which that doesn't equal x.
That's not X.
No.
And
So who tried
so you don't even have to do Goff. It's automatically no.
Oh,
Okay,
that's on the
next one.
Go.
I want a work day.
Nah,
Okay.
it's time to pick 1 minute.
Willis.
Last one.
Face.
This one's on your homework.
What?
Oh.
Let's definitely do it.
Yeah, let's do it. Let's do it.
All right, right now this is solved for area, right?
Yeah.
If I were to find the inverse, I would flip the variables.
Isn't that a circle?
It is the area of a circle, yes.
Good job, Willis.
Flip the variables and solve for a. So divide by pi, solve for the new variable. Divide by pi.
So
Maggie Horsfall, Max Kenny, Devin Cruel, Mason Adkins to the office, please. Maggie Horsfall, Mark Kenny, Devin Cruel, Mason Adkins, please come to the office. Thank you.
Square root both sides, but since we're talking about radius and circle, do we really need minus? Could we have a minus radius in a circle or a negative area? No, this right here would be the inverse. Ooh, let's do this. A to the negative first. Inverse.
Oh.
First. Oh, now we're getting fancy.
Woo! Birthday!
That's it.
I need it.
That's a lesson.
Just turn that around.
Oh. Now it's on your homework. We can go over it again tomorrow if you need to.
Nicholas Fremont, also come to the office, please. Nicholas Fremont to the office.
Why is it so
Whoa,
early?
whoa, whoa, whoa.
That's so aggressive.
Yeah, I couldn't even hear it. Bye.